one lead and then I'll start.
Okay, welcome everybody to this Google Hangout, which is week 6 of the Cancer in the 21st Century, the Genomic Revolution course. We're glad that you've come to join us either now or if you're watching this later, and we hope you find it interesting. We've got lots of questions, so we'll try and get through as many of them as possible. We've set a 3-minute time limit for each of us to speak on each of the topics, so you may hear an alarm buzzing in the background if we speak for too long. So that's just so that we can answer as many of your questions as we can. So I think Camille's going to start off. We're going to start with some general comments about week 6 and aspects first.
Yeah, so I'll just do a little revision on your peer assessments, which you did. So thank you very much to all of you who completed it. That's been very good. I think there was a bit of mixed feedback. Some of you liked doing it more than others, and some didn't have the time to do it, and that's okay, because that's the beauty of these kinds of courses, is that you can pick and choose the bits you want to do. But I think most of you really did enjoy it, and most of you said that it made you understand the subject of epigenetics better, and you like doing the research, and you spent more time even than you'd planned on doing on it. And yeah, it also turns out that epigenetics is the subject that a lot of you found most interesting in the course, so I think that was probably a good one for you to do an appointment. Sorry about the little technical issue about some people putting in just the dots or spaces or random letters. We are working with you to learn to try and fix that issue, so hopefully if you're not viewing this live but a bit later, then that issue will be fixed. And yeah, I also wanted to remind you that for those of you who think you might have to do it, and that's why you're putting dots in, that you don't need to submit an assignment to get your certificate of participation. It's not one of the requirements. And also remember that you can still do the assignment after the end of the course, while the course is still live, so you can do it after Sunday. You can still do it for quite a while. So that appears.
Okay, I'm going to talk a little bit about the financial discussion that you had. So we asked you to think about the finances of cancer therapies. Obviously, we've looked at a whole lot of different therapies and potential therapies over the weeks, and clearly there's a lot of financial implications involved in this. And you heard a bit from Phil Hanlon on the topic, so he told you about some of the ways that we look at the economics of these aspects, and then we asked you to discuss it. So I've just pulled out a few of the key themes that you've been talking about this week. There were some very good and very interesting points that you raised. A lot of you mentioned that this does depend on the health of the economy in general, so cancer therapies aren't developed in a vacuum. It depends on the country that they're being developed in, partly the country where they'll be given to people, and how the health of the economy is doing in general at that time. There may also be other priorities, so cancer therapy may not be the priority in all situations at all times. There may be other more pressing health problems and potentially other more pressing problems in the country. Also, the fact that our population is aging in general, with more elderly people, obviously there will be more cancer, but there will also be an increased risk of other conditions as well. So clearly we have to think about how resources are going to be divided up. A lot of you talked about quality versus quantity of life as well. That was another major theme that was raised. And had a think about, who should we treat? Do we automatically treat everybody? How do you decide which drugs financially are worth it, if you like, and what situations are they worth it in? Other things that were raised were the fact that these new therapies are probably likely to need an organisation at a governmental level, because it's not going to be something that's done in isolation and developed just at single level, in small places. Drug prices are likely to fall with mass use was another point that quite a lot of you brought out, and also the issue of the fact that patients are becoming more aware of treatments, so there's a greater demand on health services as patients have access to more information. And finally, I think the point that a lot of you brought out as well was that we're likely to, as well as increased costs for treating cancer, we're also likely to need to have increased costs for diagnosing as well, because if you're going to detect something, in order to treat it, that's obviously going to raise the costs in both. So in sort of summary, I think it's going to be a compromise between a lot of these different factors. Okay, Sarah's now going to say
something. So just briefly, this is the final week of the course. So Sunday the 29th is the last official date, but we just want to emphasize to you that the course materials will remain online for some time after that. Many of you are still working through the course. That's absolutely fine, including to just to access it, to make comments, and to complete any steps that you need for the statement of participation. So you can just continue to work through it at your own pace. However, we can't promise that the educators will be available forever to keep making comments in response to your comments after the end date of the course. And we will send out a wrap-up email to go out early next week with things like future resources and things that you might like to look at after the course is done if you're still interested.
Yeah. Okay. So now we'll start the questions.
Yeah, should I start with the question then?
Start.
So I'll start with one of the questions from Futurelm because we haven't got any new ones yet. So this one's from Monty Charles, and he says, I can't recall there being any discussion of the impact on cancer treatment effectiveness of the time between diagnosis and treatment. Is it possible to compare the cost of effectiveness of reducing the waiting time with that of a new drug development? I think that's a very hard comparison to make. Obviously, the earlier a cancer is detected and the earlier it is treated, the better the efficacy of the treatment. So treatments are always started or aim to be started as soon as possible after diagnosis. And that diagnosis is the important word here because the time it takes for diagnosis to be made and time between GP referral and diagnosis is just as important as the time between diagnosis and start of treatment. And that can take a long time. That can be quite significant because, as you've seen earlier in the course, some symptoms are very general and it's hard to point to cancer, and some tests can take a little longer to do as well. So we usually refer to the time between the urgent referral by the GP who suspects cancer to the time of starting treatments, because that includes both before diagnosis and after diagnosis, and that's referred to as hospital delay. And that's the important time which is important for treatment. And most studies look at delays of less than 3 months of hospital delay compared to more than 3 months and show that delays of less than 3 months are favorable for long-term survival. However, having said that, most cancers do grow quite slowly, and so a small delay between diagnosis or GP referral and treatment starting is not usually going to be the time when metastasis occurs. So a few weeks, a few days doesn't make a difference. And yeah, of course, there are more aggressive cancers, and so the key here is in being able to identify which ones are aggressive and which ones are not so aggressive, and being able to prioritize the more aggressive ones so that treatment for those is started really as quickly as possible. And that kind of accurate and quick diagnosis, I think, is going to be one of the things that's possible with genomics, as you've probably found out during the course. But having said all that, and I'm running out of time, having said all that, even patients with slow-growing cancers will still be anxious. So most governments do try and make the waiting time as short as possible to prevent anxiety. The current ones in the UK is to have a 2-month wait between an urgent GP referral and treatment starting, or 31 days between diagnosis or meeting with the clinicians to decide on treatment and treatment starting. And yeah, I just wanted to say one more thing, that these delays, it's good to keep them short, but the most important delays, the biggest delay, is the thing that we call patient delay, and that's the delay of patients not going to the GP early enough because they are not aware of the signs of cancer, or they ignore the signs of cancer, or they are too scared to go to the doctor because they're scared of the diagnosis. So that's what's being targeted with awareness campaigns by governments and things like that. And also the other side to that is alternative routes to diagnosis. So if people don't go to a GP but wait and then end up being diagnosed in an emergency, for example, then the survival is less good because the cancer is usually more developed by then. So that's more where delay has to be shortened rather than the hospital delay. But yeah, that's it.
Okay, great. So I'm going to answer the first question that I found, which is actually one that was asked in the week 3 Hangout, but which we said we would leave till week 6, so somebody reminded me of it. And it was asked by Jill Moore, and she asked, is there a direct to consumer sequencing such as 23andMe, which is currently active, and what is the status of the FDA inquiry re such companies? Now, for those of you who weren't aware of the situation, company 23andMe until last year had offered to provide basically a genetic test which would give you a risk analysis of your likelihood of developing certain conditions. And what they did was they looked at certain SNPs, which you've heard about this week, in your DNA. So you weren't having, the whole DNA wasn't sequenced, but they looked at certain SNPs, and based on some of the published evidence, they gave you a risk of what your likelihood, they said, was of developing some relatively common conditions. So you might get information back that said, you know, you had a 10% increased risk of developing, for example, type 2 diabetes. Now, the FDA stopped them testing for health conditions, although at the moment they're still able to test for ancestry. Two of the other big players in the market, DecodeMe and Navigenics, they also pulled out of the market in 2012 after they were acquired by other big companies. And at the moment, there doesn't seem to be any of the big companies offering these types of tests. I had a look yesterday at some of the smaller companies that are there. Now, what they tend to do is they tend to offer very specific tests. So, for example, there's a company called Genetic Health, which offers testing for known polymorphisms in the FTO gene and the TCF7 gene, and they give you a risk of type 2 diabetes. So it seems to be very targeted and very specific rather than this big wide range of conditions with potentially not very well defined SNPs giving you a risk. Now, apparently 23andMe, there was some information online that said they had actually put in an application to be reconsidered for some kind of testing, but I think it was only for one specific condition, again, where there's a known well-defined mutation or polymorphism. So I think the big issue here is that although these companies, the tests they were doing were accurate in that they were able to detect SNPs, they were fine at detecting them, there was nothing wrong with the tests. It's actually the clinical validity and the clinical utility of these tests that was possibly in question. How valid are the results that having a particular SNP predisposes you to, say, type 2 diabetes or to a type of cancer, because there's possibly not enough evidence. There's lots of contradictory studies at the moment, which, you know, it's very hard to define the risk, the absolute risk, based on one or two SNPs, and also what do patients do with that information. So I think these are the big issues that these companies have faced, and I think in future they'll very much tend towards offering tests for much more defined conditions rather than the generic ones. Okay, so I'll let you.
Right. So I guess we have quite a lot of questions and comments about the overall subject of diet and cancer. What I've done is split this into several different aspects, which hopefully overall should answer all your questions. So the first one I wanted to address was basically the role of specific foods in cancer. So for instance, we have Maria del Carmen Rodriguez asking about processed foods and their relationship with cancer, and Mariani Oentoro, I think, who is asking about whether there's any evidence that eating raw foods like broccoli can help slow or prevent cancer. So, firstly, processed foods. There are actually some specific processed foods that have been associated with an increased risk of cancer. In other cases, some processed foods have been proposed to be linked with cancer, but a lot of studies have shown actually there is no link. So just to give you some examples of that, acrylamide. So cooking foods at high temperatures. In the case of starchy foods, you can form acrylamide, and there's been a lot of headlines in the newspapers saying that acrylamide is a carcinogen, which it is at high levels. But overall, I mean, more studies are needed to be absolutely sure, but there really isn't any particular evidence that acrylamide from cooking foods is a major health risk to humans. What has been shown to have a link is overcooking meat. So for instance, overcooked meat, so cooking at high temperatures, things like frying, the burnt bits of the meat basically, can increase the risk, for example, of pancreatic cancer. In addition, eating a lot of processed meat is associated with an increase in colorectal and stomach cancer. We don't really know the mechanism for that, but preservatives such as nitrites have been proposed to be involved, and other preservative methods that could also introduce potential carcinogens are smoking foods and salt preservations. I think, though, overall, the balance in your diet over time is what has the greatest effect on cancer risk. If you eat a healthy, balanced diet with lots of fresh fruit and veg, and also if you take moderate or high levels of physical activity, both of those have definitely been shown to lower cancer risk. And I guess, given that I'm almost at my 3 minutes, maybe I'll talk about broccoli and superfoods later. Kimmy.
Okay, I'll maybe just take a couple of seconds to answer one question that's just come in live. So it's about Oliver Slay about, okay, I'll just read the whole question. I read that where there's a niche, stem cells will find a home, and that normal stem cell niches are generally hypoxic, which helps to prevent differentiation and maintain self-renewal. So if a tumor becomes hypoxic, might it harbor non-cancerous stem cells, such as mesenchymal stem cells, which home in on tumors as if they were wounds? Have there been any genetic studies to see if the hallmark mutations exist in all of the cells? So I've not heard of any studies looking at normal stem cells homing into tumors, but it is true that the tumors are generally hypoxic, and that's why cancer stem cells live quite well in them. Cancer cells and stem cells are well adapted to hypoxic environment. And what about genetic tests? Well, tumors are heterogeneous, so I think it would be hard to tell. They would all probably be quite different cells in there, so being able to tell which one was normal and which ones were just different cancer cells would be quite difficult. So that's that one, and then I'll find a short one. Degenking, do we know what causes epigenetic malfunctions? It sounded as if cancer cells have quite a lot of them. Could this be the cause of the cell becoming cancerous? And is it that when cancer cells keep dividing, they just accumulate more and more faults? So causes of epigenetic changes are just as varied as the causes of genetic changes, and they include very similar things such as high-fat diet, lack of certain nutrients and vitamins, nicotine, alcohol, compounds in the environment like asbestos, BPA. They all alter epigenetic tags. And of course, epigenetic tags won't just happen by magic. They happen through the action of enzymes, and these enzymes are proteins, and therefore their sequence is coded for in the DNA. So any mutations in the DNA can affect these enzymes that cause the epigenetic changes, and therefore can affect, so genetic changes can cause epigenetic changes. So it's all quite related. And then you can also have changes in the DNA sequence. So because epigenetic changes can happen at particular DNA sequences, if the sequences are changed, then more or less modifications can occur as well. And that's one thing that happens. It's not in cancer, but in Fragile X syndrome, you have multiplication of CCG sequences before the gene FMR1, and that increases the methylation, methylation at the gene, and that causes it to be silenced, and therefore causes the syndrome. And yeah, that was it. I was just going to say, for treatments with epigenetic changes, you'd have to be careful. They would have to be very selective because all the cells have epigenetic changes, and you wouldn't want to change them in all the cells in the body.
Okay. I will answer the very first question we were asked this week, which was from Rebecca Little. And she asked, how quickly is cancer treatment developing? Are there new discoveries on average every week, or less or more? It's a very interesting question. And we'll actually put up some resources for some of the questions. We'll put up some of the resources after the Hangout, or later on this week or next week, based on some of the sources we've used. And there's some really interesting ones for this question. And basically, yes, there's research being done all the time, and yes, technically there are new discoveries being made probably every day, every week, but in terms of translating these step-by-step little discoveries into actual therapeutic treatments, it does take a long while. And I was just having a look at some of the original discoveries that were maybe made even in the 1970s that are now 30, 40 years later coming to fruition with treatments. That's not to say that all discoveries nowadays take that long to come to treatments. You possibly have a 10, 15-year pipeline in some cases. But basically you have to think about what the stages are. So the pathway needs to be identified, the different molecules at the very basic stage of research. And from that, you would generally then, a target might be identified that might be a potential new target for new drugs. Once a target has been identified, then there would be the process of compound screening, so looking at different molecules, different compounds that might interfere with that pathway. And then followed by that, various compounds could be selected, and then they might be modified by chemists to make them more suitable for the purpose. Once you've got to the stage of having a compound that might be a suitable one, then it would potentially obviously have to be trialled maybe in cells, just cell culture first, perhaps animal trials. If it was shown to be a useful therapeutic potential agent, then it could be taken forward maybe to human safety trials, followed by clinical trials. So you can see that there's multiple stages. So although, yes, there are discoveries and there are things happening in labs all over the world every day, every week, that are probably novel and are being reported in scientific literature, it does actually take quite a while for some of these discoveries, and only some of them obviously will actually reach the stage where they're useful in therapeutic, they'll be taken forward to the therapeutic stage. So I think that's all on that one.
Okay, broccoli. So this question was raw foods. Do raw food diets help in cancer in any way? The example being broccoli. So basically, are there superfoods? So just quickly, cooking, especially if you overcook things, can reduce vitamins, minerals, antioxidants, etc. present in fruit and veg, as can prolonged storage. But in theory, you could be losing some anti-cancer properties. But honestly, that's not really been established in scientific studies. There are some disadvantages to eating a lot of raw foods, and notably the risk of food poisoning, which would be especially dangerous if you are ill already from cancer. And for instance, if you have a digestive tract cancer, you may not be able to eat a lot of raw veg and fibre. So again, I think basically the message is overall lots of fresh fruit and veg as part of a healthy, balanced diet. Just to take the example of broccoli, I wanted to point out that it's actually quite hard to establish whether or not there is a link between a specific food being pro or anti-cancer, and beyond any reasonable doubt, really, because it's very hard to do the kinds of studies that would actually give you good evidence for that. So, for instance, a lot of them are simply correlating populations that eat a lot of a particular food with a higher low risk of a certain cancer, and that may mean that there is no actual link. There may be a link to some other third factor that is present in that population. So for instance, people who eat a lot of broccoli might also have a lower risk of obesity, diabetes, they might have a healthier diet overall, they might exercise more, and it might be those things that are associated with a slightly reduced risk of cancer that you do find in people who eat a lot of cruciferous vegetables, such as broccoli, in their diet. It's also very hard to prove, although you can take some of these foods and extract compounds from them that in the lab will kill cancer cells. But it's very hard to prove whether or not it is those particular substances within the food that are responsible for any link between eating those things in the diet and a certain level of cancer in the population. So again, overall message, healthy, balanced diet. How long do I have left? Oh, that's it. Okay.
Good. Go for it again. So I'll answer Nuran Salum's question. And that question was, how can we make personalized medicine manufacturing profitable and economic for pharmaceutical companies? They'll surely benefit the patient, but it needs to be profitable and economic in order for the pharmaceutical industry to take this approach seriously. And would governmental research centers have the technology to produce such medications? So yeah, it's true. When you look at it, personalized medicine does seem to be hugely expensive business for pharmaceutical companies, making more specific specialized medicines for fewer, to target fewer and fewer patients. Doesn't seem to be economically viable. But there are smaller reasons. There are some reasons why it will be economically viable, and small companies and startup companies are going down the personalized medicine route. And reasons are that with personalized medicines come diagnostic tools and diagnostic tests. So companies can actually develop a drug alongside the diagnostic tool to decide if that drug is suitable or not. And then they can sell both the diagnostic test and the drug at the same time. So that, for example, the HER2 protein test for Herceptin. So that's a double income in a way. And also, as you saw this week in Sarah's talk, genomic analysis and sequencing is getting cheaper and cheaper very quickly. So it will be performed more and more, and that will increase the marketability and the profit margins and the use of personalized medicine, because finding out the mutations and the characteristics of each cancer will become easier and cheaper. Also, although personalized drugs are given to fewer patients due to their nature, they do usually have less side effects because they are more targeted and less general. And that means that you can actually give cocktail therapies to patients, giving 2 or maybe 3 or maybe even 4 drugs at the same time to the patient. And that's one big advantage of doing that, is that you're preventing resistance developing by targeting several aspects of the cancer, so it can't escape, because if it tries to escape, you've already got another drug there. But that means that each patient is getting maybe 2, 3, 4 drugs at the same time. So that increases the number of drugs that are being sold, and again, that makes it more economically viable. And finally, and probably most importantly, will be the development of new economic models. So this is a new world, and no one really knows how it will happen yet. Oh, there. But basically, companies will have to enter risk-sharing agreements between the payer and, well, I have to stop that.
Passcode.
Yeah, okay. And I've got examples of some that have been occurring already. Some work, some don't work. The governments and the industry are still testing them out. But essentially, it's where the governments and companies are sharing the risk for treatments. And an example is Aclasta from Novartis, where Novartis agreed to reimburse the cost for any patient in which the treatment failed. So the government only paid for treatment in patients in which it worked. Or they can put a cap on the cost per patient, so companies will pay themselves for any treatment above a certain cap that they've set. Or there's also an example in Australia where the company pays for a surveillance program so that they can monitor patients quite quickly and decide for whom treatment is working and for whom it's not, so that the government is only paying for treatment to patients in which the treatment is working. So yeah, basically the main aim of these kind of risk-sharing agreements is to reduce the cost of the treatment during the first few years that it's on markets until it becomes established and its clinical efficiency becomes established. Yeah, I probably should leave it at that, but I've got some nice papers which unfortunately are paid for, but it's a very small fee using RedCube, so I'll put those on.
Yeah. Right, I'm going to do 2 in my next 3 minutes so that I get through all of them. This one was asking, I can't remember who it came from, is there such a thing as a normal genome that can be used as a standard for comparison with abnormal genomes? The choice of normal seems particularly important when evaluating minor changes such as SNPs, and if there is a normal genome, what is its origin and who does it belong to? Good question. So with this, we come to the idea of a consensus sequence. Now, obviously, no 2 individuals, apart from identical twins, have the same DNA sequence. So the DNA of the Human Genome Project that was initially sequenced obviously had to come from somewhere. So where did it come from? Well, what happened was that when they were looking for people's DNA to sequence, they advertised in local areas around the labs. They recruited candidates from a diverse population, and then they counselled them and made sure they were happy to consent for this to be done. And they took about 5 to 10 times as many people's blood samples as they actually needed, and they didn't sequence one individual, they sequenced bits from different people. So essentially, it's not one person's DNA that was originally done. However, now there is wide initiatives to sequence lots and lots of full sets of human DNA. You may have heard of the 1,000 Genomes Project, which has now sequenced thousands of people's DNA, and apparently they have found, the most recent release I think had found more than 79 million variant sites. So that's 79 million places where people are different from each other. So obviously there isn't an absolute, reference DNA sequence of a human. It's the consensus sequence that may or may not be, where humans, what the sequence was originally, and people in different populations. Somebody at one position may have a T, and somebody else may have an A in their DNA, and it's very hard to tell what the ancestral allele was. Different ones have been selected for, probably in different environments. So the answer is that there's not an overall normal genome, but we do use consensus sequences to help us. Now I think I've got a minute left. I can answer my next one.
I think you can have 3.
I don't know if we've got enough time to get through them all. It says, will more research be carried out into the cell cycle to determine the best way to target personalised therapy? So for that, I thought I would just have a look on Glasgow University's web pages. Obviously, there is a lot of research into cell cycle going on, but I thought I'd have a look to see what was going on in Glasgow. So we've got a group in Glasgow, a big research centre that looks at leukemia. In particular, one of the leukemias they look at is CML, so chronic myeloid leukemia, and we know that TKIs like imatinib have been used as effective therapy for CML, but it's also been shown that the CML stem cells and the progenitor cells are insensitive to these drugs, which cause cell cycle arrest rather than programmed cell death, and that results in disease persistence. So obviously the CML isn't going to be eventually overall cured by the TKIs. So this group in Glasgow, the Tessa Hollyoaks group, looks at novel approaches using combination therapies to get rid of the stem cell population. And one of the particular things they're looking at is the mechanisms that are maintaining the CML stem cells out of the cell cycle. For example, there's one protein, FOXO, that's particularly involved, and they are looking at how targeting this protein may be a mechanism of designing new therapy. So maintaining the stem cells out of the cell cycle. This is a big area of research. So cell cycle research, loads and loads of cancer research does eventually come back to this whole issue of the cell cycle. And even here in Glasgow, you know, there's plenty of stuff being done on that. So I think that's me for this one.
Okay, so I have another couple on diet-related issues, and then I do have other questions on other things. So, several people asking, does a low-carb diet or a ketogenic diet cure cancer? Bottom line, there is currently no evidence for this. It is probably a good idea to take steps to ensure you don't have very high blood sugar levels. There is a correlation between persistent high blood glucose, hyperglycemia, and higher cancer incidence and poorer cancer outcome. But that's a correlation. That's also correlated with increased diabetes, increased obesity, changes in blood lipids, various hormone levels, etc. So the actual mechanisms involved in this correlation are as yet unclear. The idea that people seem to take from some of the metabolic changes that occur in cancer cells that we've described is that you could starve cancer cells by not feeding them sugars or glucose. That is not going to be possible because the body has homeostatic mechanisms that keep the blood glucose level pretty much constant all the time, no matter whether you've eaten or whether you haven't eaten. If you run out, if your blood glucose starts to get low, the body's carbohydrate stores are used up, the body's lipid stores will start to be used up, and eventually the muscle will start to break down also to keep the blood glucose levels at a reasonable level, because some cell types can only use glucose as an energy source. So they need that to remain reasonably high. That said, fasting can reduce blood glucose levels a bit, not down to zero or anything, but they can reduce them a bit. And notably, I think, in conditions like diabetes, where you have persistent very high blood glucose levels, that might be a problem. In order to avoid that and any potential risks from that, what you can do is minimize these spikes, these high blood sugar levels, by eating low GI glycemic index foods. If you have diabetes, make sure it's controlled. But basically, you can't starve cancer cells, and any effect of changing blood sugar levels will have an effect both on normal cells and on the cancer cells. It may be slightly more of an effect in cancer cells, but it's still going to severely affect any normal cells. Some people have proposed that ketones, which are generated when the body begins to break down fats for energy, might have specific effects on cancer cells. Currently, there is no particular evidence for that. So, yes, not really is the answer.
Okay, good. Yeah. All right. So I'll start my 3 minutes, and I'll answer a short question in a bit. So I'll just finish up my earlier question, I think, because there's just a couple of points I wanted to say. So this is the question about making manufacturing personalized medicine, making that economically viable. Yeah, the only other couple of points I wanted to make was that the main benefits of personalized medicines are for the patient and the healthcare system, i.e. the payer, and that therefore there will be increased demand. And if there is increased demand, then companies will have to, whether they want to or not, will have to go down the route of personalized medicine. Otherwise, they will be at risk of being left behind with old type general medicine that will not be better or will have more side effects than the new personalized ones. So they will have to, and the general trend is towards personalized medicine, not just for cancer, but for other diseases as well. And then for the second part of that question, which was about government research being able to do that. So there is government research such as NIH in America and MRC and BVSRC in the UK, and they tend to look at research into the mechanism that goes wrong in disease, and the research that they produce is very good at identifying targets for therapeutics. and then they tend to collaborate with industry after that, or industry takes over. And another important aspect as well here in the UK is that some charities like CR UK actually have their own drug development company called Cancer Research Technology. So they will go probably down that route as well. And now I'll answer the short question for 1 minute. So this was about the role of the mother and father in heritability of epigenetic tags. And basically, epigenetic changes are passed down by both the mother and father and by both sets of grandparents. And it's very hard to research that. And you could hypothesize that because a lot of epigenetic tags are laid down during development, during that critical period, that the mother's behavior and environment during pregnancy is more crucial than either parent at any other time. But having said that, there are studies that show that epigenetic changes can be passed down the male line as well. And I'll put up some references as well afterwards. And including one reference that tells you how difficult it is to research how these epigenetic changes are passed down, because very similar to the food aspect that Sarah was talking about, because they are affected by everything, it's very hard to isolate one element from the others. And because it's a generation thing, then it's very long-term studies, and so that's quite difficult, and it's quite a new field, so I think not much is known yet, and that will come.
Great, okay. I'm going to answer a question that we were asked, I think, earlier today, which is there seems to be a lot of interest in PD-1 in the treatment of melanoma and other cancers. How does this fit in cancer genomics, epigenomics, and the treatment of autoimmune disease, and how great is the overlap? Well, basically, PD-1, the molecule that we're talking about here, is expressed on the surface of activated T cells. So these are cells in the immune system, and it binds to a ligand, PD-L1 ligand, which a lot of tumours express. And if you have the two binding, then basically it stops the immune response being activated and recognising the tumour and getting rid of the tumour. So it's a response that we're targeting in therapy to try and get rid of this response. And one of the first drugs I think that came out, nivolumab, is an antibody which targets this PD-1 molecule, and there's been a lot in the literature and in the media about the success of this compound in particular, and other similar targeted therapies, other antibodies. And basically, so obviously this does fit into targeted sort of cancer genomics in a big way, but I think what really isn't known at the moment is why certain people respond and not others, which I think is maybe what the next stages will be with regards to the actual sort of personalised aspect of this. So we know that some people have excellent responses to these drugs, but it is a subset of patients. So a subset of patients, for example, with melanoma or with certain types of lung cancer or with renal cancers, respond excellently to the antibody therapy, but other patients don't respond at all. And as yet, there's not been reliable markers identified that can predict who will and who won't respond to the therapy. So I think that's probably where the direction of the targeted aspect of this would go. Now, in relation to autoimmune conditions, obviously you don't want your body to be recognising your own cells as foreign and therefore attacking your own cells. So there has been some work looking at whether this PD-1 molecule may be going wrong basically in autoimmune diseases, and there are some SNPs in the PD-1 gene which may be involved in this. And it has been looked at agonists of the PD-1 which stimulate the inhibitory function of it. They may be involved in, or they may be useful in getting rid of the autoimmune response, but obviously then that's going to weaken the anti-tumour response or anti-infection response that the body has naturally. So it's almost like two sides of the same coin, and affecting one could affect the other. So that's something that obviously has to be has to be looked at. And the second part of that question said, will new therapies be tailored to the genomic profile of the tumour rather than the organ of origin? And the answer obviously is yes, undoubtedly. I think will be in the future. This is how it will go. Okay.
Right, so last diet-related question. This one is from Elizabeth O'Brien. This is a very interesting one. Is periodic fasting useful during chemotherapy? Okay, so the current recommendations are that while you're having chemotherapy, you should increase your calories and protein. And it is most certainly true that long-term dietary restriction may be dangerous for people who are ill already. It's also important to know that some cancer drugs are better absorbed into the body if taken with food. So that might be one disadvantage to fasting. But recently, there has actually been some evidence published that short-term fasting, like kind of 24, 48 hours before after the chemotherapy, might actually be useful. There is some evidence to support that, especially from one American group at USC, who found that the effectiveness of DNA-damaging chemotherapies was increased in cancer cells and in mouse models of cancer by short-term fasting cycles. How would that work? Well, the idea is that the cancer cells are unlike normal cells in that they are independent of growth signals and insensitive to anti-growth signals. So cancer cells would continue to proliferate under the stress conditions that would be caused by starvation, and they would do that when they shouldn't, and therefore they would be selectively killed, whereas normal cells would just stop growing until the fasting stress had gone away. And there are a few different proposed mechanisms, such as IGF-1 levels, oxidative stress, but there are some caveats. Firstly, this research is at a pretty early stage. It is complicated by confusion in different studies between different types of dietary restrictions. So do you cut out some food? Do you cut out all food? How long for? Because all of these have different effects. It probably only applies to certain cancers. For instance, there was a paper published saying tumours with PI3 kinase mTOR pathway activation are resistant to dietary restriction. And lastly, it looked like in those studies, some of the cells actually acquired resistance to fasting as well. So the bottom line is that overall we need more research before we can answer your question. That research is currently ongoing, but will take a little while. There are a couple of other potential things to mention. There has been some suggestion that fasting might protect the immune system from the damaging effects of chemotherapy or stimulate the immune system. There's also been one very small study implying that fasting might reduce chemotherapy side effects, but both of those are very preliminary research and need to be repeated and expanded upon before we can really recommend fasting during chemo or not.
Perfect, thank you. Okay, so I'll answer the next one. There is one that's just come in. I can give a quick answer, possibly when it came in on Twitter, or maybe you can add if you want. How likely is it that cancer patients will be treated with viruses to increase immunity against tumors? And I would say quite likely eventually. You can increase immunity against tumor using vaccines, and that might come in. But yeah, definitely research to the immune system and how we can use that, I think, will be a part of future cancer care. Unless you want to add that. So I'll answer my question now. Another one. So this was one from Ibrahim Binhil Suhail. I probably pronounced that wrong, I'm sorry. It's a two-part question. Can tumor suppressor genes be given from one organism to another? Yes, in theory, there's nothing against that. Now, some tumor suppressors will be very similar between different species, and so putting one from one species into another, they'll probably have quite a similar function in another species. Some of them might be quite different between different species, and therefore, if you introduce one from one species into another, then they might have a similar function, but it might have other functions or a different function, and it's a bit more unpredictable. And sometimes some tumor suppressors do not exist in other species. So if you take a tumor suppressor gene which exists in, say, the mouse and doesn't in human, and put it into human, then who knows? That's quite unpredictable what effect it might have if it doesn't exist. Not all genes exist in all organisms. If you want to know as a therapy type mechanism, then I think you would try and reintroduce the normal human gene rather than one from another species, because they would be just as likely to be mutated as the normal human one. And that does happen for example, P53. There is some clinical trials about gene therapy, about reintroducing normal human P53. And there's even research into making genetically modified or genetically engineered P53 called super P53 that might act in a way even stronger than normal P53. And then second part, if cancer cells can produce substances that induce angiogenesis, can drugs be given that reduce it? Yes, there are a number of drugs on the market. The first one was in 2004, a monoclonal antibody. Some cancers like colon, breast, lung, bladder, renal cell carcinoma, and non-small cell lung cancer respond particularly well. However, they don't really have the unequivocal success that was maybe planned or anticipated when they were launched. And that's because tumors actually develop resistance to that. And they also have serious side effects because they damage normal blood vessels, and that cause hemorrhagic effects and thrombotic effects as well. So not the end all.
Okay, I'm going to answer one that's just come in on the YouTube site from Alexander Allenby, asking if in the next few decades do you think it's realistic that germline intervention could be used to remove and replace inherited faulty tumour suppressor genes from the embryos of genetically at-risk parents? Interesting question. Obviously, anything to do with embryos has a lot of ethical aspects to it. I suspect that what is probably more likely is that parents who are genetically at risk of having children with predisposition to cancer will probably be screened for by pre-implantation genetic diagnosis more and more. Obviously, this again is a bit ethically debatable because it's an adult onset condition, but in some cases IVF has been done, and pre-implantation genetic diagnosis has been used to select for embryos that don't have the faulty copy of the gene that would predispose to cancer. It's probably much more straightforward to do that, to pick the embryo that gets the parent's normal copy than to pick the embryo that gets the faulty copy, rather than actually manipulating the gene. I'm not saying technology wouldn't obviously be there to do that, but I suspect probably from a financial, ethical and time point of view, it's more likely to go down the PGD route. And I'll also answer one that came earlier from Aklo Oshiro, which was talking about the presentation by a young American who was 15 years old at the TED meetings. He had developed a blood test to screen for pancreatic cancer, and how did we evaluate the possibilities of that. So I had a look at some of the information on this test, and essentially it was a high school project, basically, exceedingly complex one, which for somebody of that age was very well carried out, looking at mesothelin. So it was a biomarker, potential biomarker for pancreatic cancer, and it was reported hugely in the media that this was going to be, the next big thing in pancreatic cancer, that it was much more sensitive, 26,000 times less expensive, and 168 times faster than the existing technologies. I think essentially the answer is that basically it's not been published in any peer-reviewed journals as yet, as far as I'm aware, and that it possibly is a publishable bit of science. There probably is some interesting stuff in it, but some other studies have shown that this marker isn't a specific enough marker to be used. Some published studies have shown that. So basically it probably is likely to require combining with other markers. It's probably likely to require an awful lot more work before this comes anywhere near becoming a test, if in fact it is able to be used as a test. So I don't think it's quite the big thing that it's been hyped up to be, although it was potentially a very interesting project. Okay.
Right, so I have a question from Norman Ross about antioxidants. Since antioxidants preserve cells from damage, whereas radiation kills cells, I wonder if antioxidants are helpful or counterproductive during and after radiotherapy with iodine-125. Also, do cancer cells have to be dividing in order to be killed by iodine-125 radiation? If so, is hormone therapy counterproductive? Okay, so iodine-125 is a radioactive isotope that is used in brachytherapy, where you put basically solid implants in, radioactive implants, commonly in prostate tumours and brain cancer. Now, radiation damages DNA directly, and it also causes the production of reactive oxygen species, so oxidative stress, and that damages DNA and other cellular components. Now, like other DNA damaging chemotherapies, radiotherapies work by selectively killing rapidly dividing cells, i.e. the cancer cells, but they don't need to be dividing at the specific time that the radiotherapy is administered. The damage done by the radiotherapy will happen, and then if those cells try to divide at some point after that, they would die. So hormone therapy can be used before, during, or after radiotherapy. It's often used before the radiotherapy to shrink the tumour enough for the radiotherapy to be most effective. Antioxidants and cancer are a bit of a controversial and somewhat misunderstood area, particularly in relation to supplements. It's true, I've just said, that oxidative stress and reactive oxygen species cause DNA damage. Antioxidants are agents that act against those things. So in theory, that antioxidants might be anti-cancer for a start, but also might have effects on chemotherapies that work using those mechanisms. However, in practice, any antioxidants that were to have those effects, be it anti-cancer or anti-therapy, they would need to be right inside the cell that you're talking about, and they would also possibly need to be right beside, in certain subcellular compartments. There is no evidence that taking dietary supplements will enable that to happen. And although this is definitely still under investigation, there are no studies that show that antioxidant supplements reduce cancer risk or mortality in humans. And in fact, there is evidence that taking antioxidant supplements is associated with a small but significant increased risk of death overall. So those studies have mixed results, including in some cases worse outcomes than not taking the supplements. We need more trials to be sure of whether or not they have any effects, and if so, whether they're good or bad. And I would say that there's probably a difference between taking antioxidant supplement and the very low levels of lots of different antioxidants that you get by eating a diet rich in fresh fruit and veg. So hopefully that answers both your questions there.
Good.
You got any more?
Yeah, we're coming towards the end. So we've got one, and just an interesting one that's a good ending one from Joyce Dell, who asks, apart from personalized treatment, what do you guess the future has in store regarding more groundbreaking discoveries? So I think I would say probably with genomics and better technologies, we'll have increased better screening and therefore better detection of precancerous states and therefore prevention of full-blown cancer, so that in the future will be possibly more about prevention than actually treatment of cancer. And along with that goes possibility of generating cancer virus vaccines. So I know there's a few in clinical trials, and being able to vaccinate against cancers and again prevent, so that treatment becomes not the main way of cancer care, but prevention. I think that might be the case.
Mm-hmm. I think my thoughts on that question were that probably we'll see quite a lot of increased risk prediction from SNP analysis. So instead of just being able to test for a handful of mutations in BRCA1, BRCA2, that type of gene, probably, within the coming years we'll be able to look and see SNPs which have very small cumulative effects, and be able to give people a much better risk prediction for developing certain different types of cancers, which I suppose would then feed in very much to the screening, the early detection. And I think as well, we'll probably move more from a sort of acute disease model of treatment of cancer, possibly to the more kind of chronic disease model that we see with things like HIV, where yes, there is a very lifelong condition and potentially life-limiting condition, but there may be, progressive different therapies that can be used. Obviously, we're seeing that just now with quite a lot of the new therapies that are coming up, but I think in the future that will probably be more how the direction that it moves in, I would imagine. Any thoughts?
Do we have time for any more questions?
Yeah, did you take notes on live questions? Do you want to?
Well, I had one. Time?
Yeah.
I had one.
It's 8.
I could do 1 more minute on my other questions,
Yeah.
and you could do one more on yours.
Okay, so we have a question. Well, it's partly a question from Mike Wooder. Please can you comment on the possible utility of epigenetic therapy to attack cancer stem cells, assuming that we can induce them to divide? So cancer stem cells, the idea is that they're a subpopulation of cancer cells with distinct stem cell-like properties, and that these ones would be responsible for both initiation of the tumour but also metastasis and spread. They are resistant to the conventional therapies that would be used to treat the rest of the tumour, and you would need specific therapies to target them. So would epigenetic therapies be useful? Yes, in the sense that stemness, both in adult stem cells and in cancer stem cells, is controlled in part by epigenetic modifications. You wouldn't necessarily need to induce cancer stem cells to divide in order for this to work, unlike the conventional chemotherapies. But I think one caveat to that is that many of the agents that we currently use for epigenetics, they're not very specific. They alter in general in lots of cells, like histone modification or methylation, acetylation, etc. So we may need to find ways to target epigenetics more specifically before we can really use it in therapies. But there is the potential for that, and that of course is because epigenetic changes are reversible in an individual cell without that cell having to divide, etc., whereas the genetic changes are not. And that's related to the question that we got on Twitter, which is, can stem cells help cancer patients in the future? I think, just to be brief, firstly, stem cell research will most certainly help in the sense that it will help us understand cancer and cancer stem cells. In terms of treatment, well, we already do have bone marrow transplants, for instance. If a tissue is lost because of cancer or because of cancer therapy, you could potentially use transplanted stem cells to regrow that tissue, such as is the case with bone marrow transplants. Hopefully that helps answer those questions.
We've got one tiny question here which I'll not actually answer, but I'll point you to a resource, which was, how will nanotechnology impact on cancer diagnosis and treatment? And the answer is there's a lot of very interesting work in this field, and we'll put up a resource for that. It's from cancer.gov, which talks about all kinds of aspects of nanotechnology, which I found a very interesting subject to research. So it's just something a wee bit different that was asked, so that was good. We'll also put up a transcript of this Hangout, possibly not till next week, because unlike the videos, the Google Hangout transcript has to be done by hand, so it takes quite a while to do it manually. But I think that's everything. There was excellent questions that were asked.
Yeah, thank you for all the questions.
Yeah, it's very good. It's very interesting investigating all the different questions. For all your contributions, and hopefully lots of people will watch the Hangout video when it goes onto YouTube.
Yeah.
And I think anything we haven't had time to cover, we can potentially reply to in the comment sections on the actual Future Learning course. Yeah. So thank you.
Okay,
thank you very much.
Bye-bye. Bye.